Hi, in this session we're going to be looking at the issue of the communication of design intent. Design engineers need to find a way in which they can communicate their ideas to other people, primarily to manufacturers. So how do they do this? How do they tell the manufacturer what to make? They can't do this simply in words, particularly with complex products. They have to find another way. Another issue is that the design engineers often don't know the best way of making things, and they may produce designs that are either cannot be made or are very expensive to make. And therefore the communication isn't necessarily one-dimensional, but could be bidirectional, from the designer to the manufacturer and back, and it may be iterative. So we'll look at the issue of the translation of the information, and it's an important issue because, like any translation, there is always the risk of error. Types of things that can go wrong are that we have missing features, for example a hole that doesn't get drilled or gets drilled in the wrong position, and therefore we have issues to do with dimensions and tolerances. We can also have the problem of selecting incorrect materials, and whilst these can be overcome in time, there is always a risk that they may find their way through to the users. For some this will be inconvenient, but for others it can be tragic, can even result in the loss of life. So this is an important subject, not only for commercial success, but also in case of litigation. Through history, design has typically been communicated through the use of drawings. These can range from simple sketches through to more complex engineering drawings. But essentially they are two-dimensional models of what in the real world is actually a three-dimensional item. Therefore, the designer, or the person creating the drawing, has to choose a viewpoint, a particular view on which to present their information. And this is limited. There cannot be an infinite number of viewpoints, there just isn't the time or the paper available to do that. As a result, the design information is not always clear. And this can really lead to the mistakes we've talked about earlier. Engineering drawings are a formal way of representing two-dimensional information, or three-dimensional information on a two-dimensional surface, and they do this through the use of projections. Typically there are three projections on orthogonal planes, viewing the object from the side, from the front, and from the top or the bottom. But as I've already said, there are a limited number of views that we can make. Whereas it may be possible to represent this information for simple products quite well, for complex products it's very difficult, and it can result in many views, large drawing packs, and expensive control procedures. Nevertheless, we can still have incomplete design data that leads to errors in manufacturing. Since the 1980s, much more use has been made of 3D models with the evolution of powerful computing technologies. A 3D model is more than a drawing. It is actually a representation of the 3D part, which can be viewed from the side, from the top, from the front, in fact from any angle. And this allows the manufacturer or the supplier to better understand the intention of the designer by viewing a close view from far away, or even sometimes from inside the product, to understand the intention. It's also easier for us to assess the impact of changes. We can look at products in their environment, their packaging with other products, and their relationship in assemblies. And this reduces the cost of making changes and speeds up the process of new product development. So let's take a little while now to look at the creation of some simple 3D geometry. So this is our CAD design. I'm going to start by sketching a rectangle on a plane. I'll do that quite simply by clicking the opposite corners of this particular object, and you'll notice some constraints appear. The next step is to dimension the sides of the box. I'll make that 70, and I'll make this one 80 millimeters in dimension. It's by default I drew it as 100, so I'm just going to reduce that down to 80 millimeters. I type that in the box, and there you go, the size is reduced. Okay, the next thing is I'm going to put a little hole in the top right hand corner of this plate, and again I'm going to dimension it. This is design, not drawing, so I'm going to specify the size. I'll make that 15 millimeters outside diameter. I've done that now, and I'm going to flip it into 3D view to have a look at it and give it some thickness. I'm going to accept the default thickness, which is what we see here. It's 20mm thick plate, and we'll just have an inspect. There's our basic plate. So the next thing I want to do is put some more detail on it. So I'm going to select a surface. Whoops, not that. Let's try that again. Make sure I select the surface, go into the sketcher, and again I'm going to draw a circle which will become a hole. Now I know that when I'm going to create an assembly there's going to be a pin here, and I know the pin dimension, the diameter of the pin is 15mm, so I'm just going to resize this hole to a diameter of 15mm, like so. And the next thing is to set that hole in the right location. I've just drawn it there, but I want to use dimension constraints to offset it 20mm from the left hand border and 20mm from the bottom border. So I just apply a constraint from the centre of the hole to the edge of the plate, and I put that in as 20mm. There's my hole offset, and the next thing is let's make it a hole. To do that I'm going to go back into the 3D view and give it some depth. I'm going to put a hole constraint in here which is going to go through to the last surface, the far surface of the object, and you see it punch through there to the far surface. It's not dimensioned, it's specified up to the furthest surface, and the CAD tool knows where that is. Now this hole is actually going to sit in a slight pocket, and the pin will sit within that. So I'm now going to put in another circle, again, a bit of geometry here, and give that a dimension. I know the pin is about 50mm, so I'm going to make that 58mm diameter. And finally I'm going to go back into the 3D view and give it a depth of just 5 minutes, not up to last now, but a specified dimension of 5mm. So just type in 5mm in the depth field, and there's my plate completed, which I'll now save. And this is a CAT part. So it's an individual component part. The next thing we're going to do is create an assembly, which is actually called a CAT product file in this particular tool. So I'm going into my assembly design tool, and for this particular assembly I'm going to insert two components. They're existing components. It's the plate 2 that I just created, and also a pin which I've drawn already. So I'm going to insert another existing component, pick up the pin which is there, load it in, and you'll notice it will be coincident the datums are in the same place. Now I could just drag this component around and locate it by eye, but in fact I'm going to use a constraint, a coincident constraint, to align the axes of these two hole features. And finally I'm going to set a contact constraint to place the surface of the pin against the part. Now that's the wrong side of the part, so I didn't do that right. So I'm going to go back and I'm going to remove that constraint by undoing it and try again. This time I'm going to grab that surface, the bottom surface of the pin's head, and then spin around and choose the inside surface, and it snaps immediately into position. And there's my assembly. As I said, it's not just items located next to each other, they are actually constrained to be in that, and that's the design intent. That's what the designer has decided, and here I'm just going to save that as plate assembly CAT product. That's an assembly product. Few people on the shop floor actually have access to 3D graphic stations which would allow them to explore a 3D model. Most people on the shop floor still require access to drawings, and so therefore we can now look at how we can convert a 3D model in CAD into a set of drawings, a process known as drafting. In fact, in traditional engineering, we don't have a 3D model. We start straight away, the design engineers start straight away with a drawing. So we're going to load our plate model, which we see here, and we're then going to use that to create a drawing. We're going to draw out some of the pertinent features and dimension them. So I'm going to switch to the drafting tool, and I'm going to select a layout. There are various types of layout, different standards that people can use, and you can show more or less information as you need. So here's some basic information. It's showing 3 elevations, a front view, a left view, and a top view onto the part. And for each of these views I can select some features, an edge, a circle, a hole, and create some dimensions. Now these dimensions aren't essentially created by me. All I'm doing is I'm choosing to illustrate features of the design, and I can have as many or as few as I choose. I'm just going to set up some basic ones for the depth, width and height of the plate. So I'm just going to select the final of those edges. I've got 80mm by 70 by 20. Those are the outside diameters of the outside dimensions of the plate. And I'm now going to just pick up one of the hole features, that 15mm hole that we saw earlier, and I'm just going to grab that and illustrate it. I'm not designing here, I'm simply drawing. I'm exploiting data that's already in the CAD system and just presenting it. There's a certain amount I have to choose about where I'm going to position things to make it readable. I'm just going to put on the two key dimensions here of 20mm from both of those edges for the centre of the hole. So I'm just going to pick the right surface, that surface there, to make and draw that out to the side so it's readable. And I could do the others, but I'm not going to bother you with that. I'm just going to load in another version of this with a slightly more views, so you can see that there's a choice that anyone has as to how much information they want to show their clients or the engineers that are going to use this information. I've now got front views and rear views and bottom views. But the feature I want to show you now is that we can exploit the information in the CAD system to show another type of data, which is called an isometric view, which some of you may have seen. And some of you may even know how to do this by hand. And the computer makes it very easy, and obviously in a complex design we might want to show many different isometric views of the component or of the assembly from different users' perspectives. Although we may have a 3D model of a part and associated drawings to communicate this to shop floor and to supply chain, it isn't just about the geometry of a part. We also need to communicate information about materials, dimensions, surface finishes. We may even need to communicate information for health and safety reasons. And of course, we'll typically also want to identify who the originator of a design is, when they created the design, and particularly importantly, what revision the design is at, given that most products evolve through time, and so drawings and 3D models in fact change as a result. So this information is typically not recorded on a 3D model, but is associated in a number of files or in a database, and we'll look at systems for managing this information in an integrated way in another session. In summary then, the use of 3D models is now widespread within design departments, even in small companies, but it is still growing only slowly in associated departments, for example in manufacturing departments. 2D drawings are still used, and as a result we will still need to check to confirm that what has been made meets the intention of the original designer. And this introduces additional delays and costs in processes like new product development. What we do know is that the best firms achieve their competitive advantages through a combination of resources, and one of these is the use of shared 3D models. If we can introduce 3D models in other departments, particularly in manufacturing, then we reduce the chance of errors in interpreting design information and speed up the process of introducing new products and making changes to existing ones. And we'll look at these issues and the use of 3D models in other areas in other sessions.